Here are solutions to homework set number 8 for ECE 341. This homework set covers gamma, Poisson, and normal distributions. Now the first problem is, suppose I have A is an exponential distribution with a mean of 10 seconds. For example, this could be the length of a telephone call, the time until the next customer arrives at a store. Let B be the time until 3 customers arrive. So B has a gamma distribution, A has exponential. Number 1, determine the PDF for B using Laplace transforms. Well, in this case, I know A has the following Laplace transform: 1/10 over s plus 1/10. That's for 1 customer arriving. For 3 customers, it's that multiplied 3 times, or that cubed. Take the inverse Laplace transform. Here I'm going to use a table of Laplace transforms. From the table, 2 over s plus b cubed gives you this. Put it in the same form, pulling out the 1/10, and then a half to give me the 2 up on top. This has the inverse Laplace transform of t squared e to the minus t over 10 times 1 over 2000. So there's the PDF. At 20 seconds, I should have 0.0271. Problem 2 is check your answer using convolution. So if I have time going out to 100 seconds, here's the PDF for an exponential with a mean of 10 seconds. Convolve it, I have 2 customers. Convolve it, I have 3 customers. Truncate it so that the dimensions of t are the same as b. And at entry number 2001, I'm at 20 seconds. At 20 seconds, I'm at 2.71%. Same as problem number 1. And if you're curious, that's what the PDF looks like. This is the PDF for 3 customers arriving. Now, problem number 3 says, what's the probability at 20 seconds? Or what's this area? There's a couple ways to do that. One, you could use the Poisson PDF. The Poisson PDF is actually discrete. It's lambda to the k e to the minus lambda over k factorial, where lambda is the expected number. So I've got 20 seconds. On average, customer arrives every 10 seconds, so lambda is equal to 2. Plugging in 3, I get 1 over 3 factorial, 2 cubed, e to the minus 2, or 18%. That's one approach. The second approach is integrate this out to 20. I can use numerical methods. I could use Laplace transforms. Using Laplace transforms, here's the PDF. If I integrate, I get the CDF. Using partial fraction expansion, let's see, eventually I wind up with this for my partial fraction expansion, giving you these terms. Take the inverse Laplace transform. I'm seeing a 2 right here. And I get the CDF is right here. Plug in 20 seconds, I get 32.33%. Second way is use numerical methods. Come up with A using convolution. Now do numerical integration. I get the same answer, 32.44%. Pretty close. Again, I've got a little bit of error due to my step size. Make dt smaller, it'll be closer. Problem 4. In D&D, you roll a 20-sided die. If you roll a 20, you automatically make your saving throw, whatever it is. So use a binomial PDF. Determine the probability of making 4 saving throws in 20 rolls. So that would be, I've got 20 rolls, choose 4. Probability of success is 1 in 20. Probability of a failure is 19 in 20. Multiply it all out, it's 1.33%. That's the actual probability. A Poisson approximation approximates it with lambda is n times p. That's the expected number of successes in 20 rolls, 1. F of x is then 1 over x factorial, lambda to the x, e to the minus lambda. Plugging in lambda is 1. x equals 4, I get 1.5%. A little bit off, but fairly close. That's the Poisson approximation for binomial. Okay, so that was a gamma and Poisson distribution. Number 5 and 6 deal with the normal distribution. A property of normal distributions is when you add a normal to a normal, you get a normal distribution. So if I take x and y, add them together, the means are going to add. The mean becomes 25, and the variance adds. That's the oddity about normal distributions. It isn't the standard deviation that adds, it's the variance. So 6 squared plus 8 squared is 100. Take the square root 10. So x, or f, the sum of x and y, f has a mean of 25 and a standard deviation of 10. It kind of looks like this. Means 25, and the spread is 10. So here's 15, here's 35. What's the probability that f is greater than 40? So if I take the number 40, and take the area to the right, I'm not exactly sure why I did 40.5. No, it should just be 40. Okay, let's change the problem. 40.5, there. Take how far the threshold is from your mean in terms of standard deviations. That gives you your z-score. Using a normal table, I can then convert that to a probability. So the area to the left is 93%. The area to the right is 6.6%. I can check that with the Monte Carlo simulation. If I run this and check, it's 6.7%. A little bit different, mainly because I made a mistake here. It should be 40, not 40.5. Number 6, if I add 3 normal distributions, normal plus normal is normal. The means add, so the mean becomes 45. The variances add. Variance is 200. Take the square root, I get 14. The z-score for 60, these 0.5s keep sneaking in. Z-score for 60 is 1.06. I'm using a normal table that corresponds to an area of 85%, or 1 minus that, 14%. So 14% chance the sum will be bigger than 60. Check that with Monte Carlo, I get the same answer, 14%. So that's homework set number 8 for ECE 341.